for all of us, especially in the field of education. We are coming so close. I wouldn't have dreamt of meeting you and interacting with you had it been not a COVID scenario, I think.
Yeah, it's certainly been a challenge, but we're learning a lot of new ways to communicate with each other. I think is good.
Yeah,
Definitely.
it forces us to find new ways to communicate. That's one good thing that happened out of the
In
situation.
some ways, it's making the world smaller in some ways. So
Yes.
So Dipti has about 100 students on and teachers on from India.
that's
Yes,
amazing.
they're
Thank
About
joining. They're
100.
all very excited. And there was a very interesting project that I started with my students very recently. So I took them to a virtual tour to Antarctica, where they could, see the icebergs and the flora and the fauna and the animals. And we spoke a little bit about the various phenomena that takes place in Antarctica. So I have raised that curiosity level in the students, and today they are really, really looking forward to listening to you and gaining from your experience as to what it is uh, to study about Antarctica and all the
Right.
minute descriptions and details.
Good. Well, we'll tell a few stories, and we found that with 3 speakers, we have to really compact it and be right on time. But I think it'll be good. We're going to talk a little bit about what it's like to live in such a crazy place, live and work in the extremes of the polar regions, and some
So,
science.
what was the time duration you were there in Antarctica?
I went twice, and I was there in 2002 from about end of November to beginning of March, and
Okay.
for a long period of time. And then the second time, a little bit shorter, we went in bef- in about beginning of October, I think it was, and got home before Christmas. So about 2 to 3 months each time, and it takes probably 10 days on each end to get there and get home. You can get weathered in, so you have to plan on an extra 10 days for travel on each end of getting there. So, and I'm going to Greenland.
Very extreme conditions.
Yeah, and I go to Greenland next year, so I'm looking forward to that. Excited.
So, isn't the living and you must be facing lots of storms and everything out there? Must be a real big challenge, right?
In Antarctica, we're going to talk a little bit about that, but it's the extreme cold and it's very windy. So sometimes you can have just extreme conditions that make it very difficult to work outside. But yeah, you adapt pretty quick. My husband said when I got home that I wanted to keep the temperature down where he could see his breath in the bedroom. It wasn't that bad, but he thought it was. It took me a while to get over, needing it to not be so hot. Excuse me. So, where in India do you live?
We have our school in Raipur. That's exactly the heart of India, Chhattisgarh.
Okay.
So if you know a little bit about India, it's the Bhilai steel city.
Okay. And all your students are from that area?
Pardon?
Are all of your students from that area?
Yes,
Yeah,
they're all locals from that area.
Okay. And what is the weather like there?
It's extreme in both the seasons. So it's like extreme hot and extreme cold.
Okay.
So yeah, tropical.
I lived in Chicago, outside of Chicago in Illinois, and it was like that. We had extremely hot in the summer and extremely cold in the winter. So I kind of understand that.
So right now you are in which part of America?
I'm in Florida now. I live in
Florida.
South Florida. I grew up in Florida, and then we moved back down here when I retired from teaching. I taught for a lot of years, and then we retired down here. And so I had worked for a science research team then retired from that and came here, and then had the opportunity to go to work for the ice drilling program. So working on my third retirement. so, so
Wonderful.
it's been a great opportunity.
And today we have the great opportunity to learn from you.
Well, I hope so. Let me check.
And I really thank Dr. Philip and Professor Sen for organizing this for the students of Chhattisgarh, getting everybody together and trying to share our experiences.
Impressive. Very impressive.
Very impressive.
I'm going to mute myself for a minute and call Bill.
Yeah. Perfectly fine.
So I was talking and muted myself. I'm going to call my co-facilitator and make sure everything's okay because he was going to be on by now. So I'll be right back.
Hi, Bill. Oh, I think you're muted. I think you're muted, yeah. Okay.
I got time zoned myself out of.
Are you in Antarctica?
Oh man. Best, all you can do is practice, practice, and then you forget about the time zone. So, how should I I have another computer that I'd like to get on also. Should I log on the same link?
You try that. You might want to try it. You might should work.
Okay.
President is not here.
He's getting into his office. He
He'll be joining.
at a conference call because we just got some food donation for our students. So, but he's on his way right now.
Okay.
Okay, so should I invite him to talk by the time if I see him? Because
Yeah, you can do that. I think he's getting everything situated, but yeah. Let me
Abhishek is here,
my
Professor.
computer in
Abhishek
case-
is here also. Abhishek from India is here, from IIT Mumbai is here. Professor Abhishek, hi, good to have you on. Sanjay, good. Yeah. Paramita.
hi Sanjay. Yeah.
Hi, Sanjay.
Paramita, you can get started if you know. You can get started.
Okay, so okay, so I'm starting. Okay.
Yeah.
All right. Welcome everyone, and I'm Paramita Sen from Department of Chemistry, Earth Science, and Physical Science of Bronx Community College, and welcome to this webinar on climate change and ice core study. Climate change is a buzzword now, and the effect of climate change is felt all over the world. We living in cities are facing multiple environmental shifts. Climate models have predicted that we'll have a more climate change will bring actually more higher temperature, more heat waves, and precipitation. And in response to the trajectory of the greenhouse gases, they have also predicted that we'll have a more sea level rise, and as the ice of or the glaciers of Greenland and Antarctica are melting, and that's a frozen part of our Earth. I mean, it's holding about 1.8% of the hydrospheric water. That's a cryosphere. So we are fortunate enough to have this webinar with three top scientists. One, Bill Grosser from Dartmouth College, who has done a lot of work in
Bob Hawley.
Bob Hawley from Dartmouth College, who has done a lot of work on Greenland and Antarctica and glaciers. I will introduce him in a couple of minutes. And then we have Louis Hoffman and Bill Grosser from School of Ice. I was very fortunate to have taken a workshop, and that's how I got introduced to them in summer. So before I introduce them, I'd love to invite President Sekin Egbe and Provost Lester Rapallo to share a few words with us. They're always very, very encouraging and supporting for any academic endeavors.
And collaboration that brought this new weight of communication that we have, that the pandemic has brought us. We're using these channels to communicate. So thank you all. On behalf of our CUNY family, our president, Thomas Sekin Egbe, I want to say thank you, and I look forward to this wealthy and healthy discussion on climate change and what we can do as a system in here in CUNY, and also our students, and working with Mr. Chantney and his collaboration and wonderful partnership. So thank you so much.
Thank you, Professor Rapallo. Paramita?
Yeah, if President is not here, I'd love to have Dr. Philip, the chairman of our department, to share a couple of words with us.
Sure. Thank you again. This is a great event. I see Louis sitting there, and I took a class with Louis back in 2016, I think it was. We love to do things on ice, and I would love to go to Antarctica and take our students there. That's the more important. Everybody wants to go to Antarctica. But we have done a lot of things at Bronx already in CUNY, and we've taken students to catch clouds, for example, in Colorado. Yeah, you see our students in Stone Peak Lab in Colorado, 10,000 feet in the mountains. It's Roberto catching clouds and monitoring climate change through clouds, And you can see collecting cloud samples here. This is a lab we go to up there, 10,000 feet in Colorado. These are the students. They come from all backgrounds, all walks of life. This is Dr. Heinemann, my mentor. This is, again, an example of our students doing work on climate change through clouds again, looking at up here, down there, there's clouds down there, the snow is up here. So this is, again, this is a great event to culminate. And we also do a lot of things through students again, and we have a greenhouse gas monitor on top of the roof of one of our tallest buildings, Meister Hall, where we collect our student, Alejandro Prieto, help us set up a Picaro instrument. We got a big grant from the university for Picaro to collect gases that monitors climate change. You can see this is the instrument this is the results. It tells you about carbon dioxide, methane, water vapor. And when I went to Colorado with Luis's program, I saw the same instruments in Colorado at INSTAR University. INSTAR, these top institutes are the mountains that does a lot of work on climate change on the Antarctic. So we have the same things at BCC, and so we're trying to really push the envelope. And this is a record. So we have a lot of data, and we're really happy to talk about Antarctica, and Louis and Bob and Bill. These are the experts. So we're going to hear it from the horse's mouth from them. So thank you, Louis, Bob, and Bill, for coming on board and sharing with us, all the knowledge that you have and all our students. Thank you.
Bob Hawley is a geophysicist, and he's the chairperson of Earth and Physical Science Department in Dartmouth College. He had his PhD from Washington State University and postdoc from Cambridge. He has several articles published in various prestigious journals, and his main interest is studying interpretation of ice core and balance of large ice sheets, which actually is very interesting, remote sensing. And his workplace is east and west of Antarctica and Greenland. That will be very thrilling for us to see his workplace. Louis Hoffman is an educator. She is also one of the presenters today, and she has focused on polar science and climate studies. She is a director of education and outreach for US ice drilling program. She has won several awards, like Golden Apple Award of Excellence in Teaching in 2003. 2001, she is among the who's who among American teachers. And we have Bill Grosser, who is an educator in chemistry and physical science. He has won several awards. Some of them are Radio Shack Technology Award. And 2004, Bill Grosser got the Golden Apple Fellow Award. So we are fortunate to have all of them and looking forward for a very, very informative webinar.
Yes, we'll take a minute and recognize two of our participants from India. They have a lot of students on with us here today, Dipti Tiwari and Yashni Pachkana. Could you say a couple words, Yashni, and just, Dipti, really fast?
Sure. Thank you all for having us over. We have a lot of interest in environment and environment sciences. We have a small orphanage and we have all the children from our orphanage here right now listening to you all. We run an eco village which won the UN award for environmental sustainability way back in 2017. And we are now impaneled with the UN environmental, UN UNEP as well for water conservation. We have the largest water conservation program in the area. We are also doing a lot of work with rural development, and now we've connected with CUNY and other universities to do a lot of collaborative work for in sustainability, basically giving students a very hands-on approach to where climate, economies, and everything kind of coexist. So we call it a green economy, and we like to work on circular economies and so on and so forth, looking at the impact of environment, how spaces like us, especially overpopulated countries like India, China, developing nations are contributing a lot towards pollution, and how we can minimize it right from the grassroots level rather from the cities, because if it comes from the grassroots, it kind of resonates in the cities as well. So thank you again. It's a real pleasure, and I'm really looking forward. As a kid, I've always been looking at Jacques Cousteau's diving videos, and that's where I've been brought up. I lived in Europe for many years, in the US, Singapore, and I've seen the shift in weather from snowstorms to really hot summers in Europe, and I feel it's high time, you know, we really do something about it, and I'm looking forward. Thank you again.
All right, Dipti, really quickly, a couple words. Thank you, Ashneet.
Thank you. Thanks, Paramita.
Thank you.
Thank you, Neil, and thank you, Paramita, for giving us this opportunity today. My students, my teachers, our honorary secretary, Mr. UK Mishra, principal, Mrs. Fool Mali, they're all present here with lots of enthusiasm because it's a very unique opportunity that you all have provided to all of us. Right now, we have been doing projects, but this time I personally took them for a virtual tour to Antarctica, and they have slight, inputs as to what you all are talking about, but to get the finer details from you so that they can embark on another virtual research program to learn more about what it is to be in Antarctica and how you all are making a difference trying to study the climate, the history of the earth. So with your experiences, they're going to learn a lot. And I really thank Provost Rapallo and President Sekin Igbe for giving us this opportunity. Thank you so much.
Thank you, Dipti. Paramita, I'll pass it back to you.
Yeah, so we can start now. I think we'll start with Louis Hoffman and Bill Grosser.
Yes, and just a quick little thing, Bill. I don't know if anybody on here who's running this, if we were going to post a link into the chat box, but
Yeah.
it's not allowing me to post it. Oh, wait, yes, it is. I
You
see.
can
all-
post. Yeah, you can post.
Okay,
You can
All
post,
right.
yeah. Please post it to all panelists and participants. Yeah.
right now, I missed that
Attended.
link. That scared me for a second. Okay, I'm going to share my screen now. And I don't have a second screen. Can you see it?
Yeah.
Okay. So my name is Louise Huffman, as Paramita said, and working for the ICE drilling program, which is also known as IDP. We're going to be talking, Bill and Bob, with me today about climate change monitoring through ice cores in Antarctica and Greenland. But before we do that, I kind of want to take you on a little fun trip to Antarctica. It's a short video. And while you watch this, I want you to be thinking about what working and living conditions are like in such an extreme place. Also, how is travel between the bases and field camps managed? There's some interesting adaptations that are needed for that. And what adaptations are needed for humans to survive in such a place. So we'll watch this video.
Let's have bizarre celebrations. Let's forget who, forget what, forget where. We'll have bizarre celebrations. I play the Satyr in Cyprus, you the bright being stripped bare. Let's pretend we don't exist. Let's pretend we're in Antarctica. Let's pretend we don't exist. Let's pretend we're in Antarctica. Let's have bizarre celebrations. Let's forget when, forget what, forget how. We'll have bizarre celebrations. We'll play Tristan and Isolde, but make sure I see white sail, sail. Let's pretend we don't exist. Let's pretend we're in Antarctica. Let's pretend we don't exist. Let's pretend we're in Antarctica. Maybe I'll never die, I'll just keep growing younger with you. And you'll grow younger too. Now it seems too lovely to be true. But I know the best things always do. Let's pretend we don't exist. Let's pretend we're in Antarctica. Let's pretend we don't exist. Let's pretend we're in Antarctica. Let's pretend we don't exist. Let's pretend we're in Antarctica.
So hopefully that gives you a little taste of what it's like to get to Antarctica and what it's like to get around in Antarctica. Those were taken when I worked for Andrill and was down in Antarctica. I've been lucky enough to go to Antarctica twice. Antarctica is an amazing continent. So I want you to kind of think about what you notice in that. And I'll want to tell you a little bit about Antarctica. It's a continent with an amazing global peace treaty that protecting it for peace and science purposes only. It also is a continent of superlatives. It's the highest, driest, coldest, windiest place in the world. And I was lucky to go to Antarctica twice in 2 different research teams. Once in 2002 at a remote field location in the Dry Valleys where I slept in tents. It was there that I experienced the extreme cold for the first time. My first night in a tent, it was minus 40 degrees below zero. By the way, you know, I grew up in Florida and moved back after retiring. So this was, and I'm not much of a camper. So this was way out of my comfort zone. That night I shivered and shook in my sleeping bag and asked myself the question, what have I done? I asked to be here and I have 2 more months of this. It did get better. Temperatures got up to 15 above zero, which is 9.4 degrees Celsius. And we felt it was a heat wave. So we adapted to the cold pretty quickly. The coldest temperature ever recorded on Earth was in Antarctica. It was minus 128.6 degrees Fahrenheit or minus 89.2 Celsius. Antarctica is also a cold desert. It gets less than 2 inches or 2.54 centimeters of precipitation a year. And that desert is the driest place on Earth. Gets less than the Sahara Desert in precipitation. People get a lot of problems from that dryness. Your lips get chapped, your skin gets chapped. If you get cut, your skin doesn't want to knit back together. It needs moisture to do that. So you always walk around with lip balm and hand cream and a bottle of water to drink because of all that dryness. You saw a lot of different ways of travel around Antarctica. It kind of depends on where you're working. In the remote field camps, we took helicopters out to the field camps and then mostly walked, carrying 70-pound backpacks, walked 14 miles some days to get to our field places where we were doing the science. If you're in McMurdo on base or one of the other 2 US bases, we got around, you use helicopters or tracked vehicles like you saw in the video. And the adaptations that humans have to survive really depend on your equipment. You want the best sleeping bags rated the coldest that you can get. You want the best tents to keep out the wind and your clothing. And the National Science Foundation does a great job with our equipment. So I want to say to you that climate change is happening now, and you can see it in your everyday life. Humans are the main cause of it. And action taken today can limit future warming, but the time is short. Today's generation is the first generation to feel the impacts of climate change and the last that can do something about it. That quote is from NOAA, Teach for Climate, and I think that's a pretty powerful quote. So is there a difference between weather and climate? I like this quote from Mark Twain. I think it explains it really, really well. Climate is what you expect, weather is what you get. Weather can change in the order of minutes to days. When I was living outside of Chicago in Illinois, we would get minutes, maybe 5 minutes to take cover because a tornado was coming. In Florida, we get 5 to 7 days, maybe 10 days to get ready for a tropical storm or a hurricane. But weather is pretty short term. Climate is the average of the long term. So 3 decades of weather defines climate change. And on the decades, like 2000, 2010, 2020, those climate definitions are tweaked for different regions. In 2010, I remember that seed packets, which had been pretty much the same for as long as I knew, and if you plant any plants and get a seed packet, sometimes on the back, there are growing zones. And those growing zones had to be changed in 2010 because plants, it's warming farther north, plants can grow farther north. So ice cores, I work with ice core scientists and try to help them communicate their research. They're understanding the past to better predict the future of climate. So what can ice cores tell us about past climate? And how do scientists use evidence from the ice cores to understand how today's climate compares to the past? So I love the fact that in the IDP program, science and engineering comes together in a great way. It takes engineers to create the drills for the scientists to be able to do their work. So scientists, drillers, engineers work together to retrieve these ice cores. We have a big stable of ice drills. We have hand augers take very small ice cores and can just be done with your hand. We have what we call agile drills that can be moved easily by human power across an ice sheet, taking ice cores along the way. And then we have the giant blue ice drill that takes ice, that can get an ice core down 1 to 2 miles in the ice. So really long ice cores and long history of climate. For those of you that live in places where there's snowfall in the winter, you know that snow falls, and usually in spring and summer it melts. But in Greenland and Antarctica, you get snowfall and it doesn't melt. The next year, another snowfall. So it builds up layers. So in this cartoon, you've got snow at the top, and then as the snow gets heavier and heavier and compacts, it becomes firn. And within firn, that's the older snow, air is able to still move with it throughout. It's porous. But at the firn and ice transition, there's so much pressure that it traps those air bubbles in ice, and the air can no longer move through it. And those air bubbles literally trap a record of what the atmosphere, what the concentration of greenhouse gases was in the atmosphere when that snow fell. And that can be hundreds of thousands of years old. So when scientists are retrieving an ice core, sometimes they will dig an ice pit, like the picture on the left. And behind that ice pit, they'll dig another ice pit to let light in so they can see the layers of the ice. And they're able to learn a lot of very interesting information about dust blowing on ice and windstorms and all kinds of things by looking at these layers in the top of the ice core. That beautiful picture in the center there shows some really nice layers of ice, but you also see a volcanic layer. And within this ice, you have anything that's in the atmosphere, isotopes from nuclear reactors or explosions. You can see volcanic ash like in this one, and that helps date the ice cores. In the middle bottom and the very bottom, you're seeing layers, dark and light layers in the ice. Winter and summer snow has different densities. So they look light and dark. The light and dark layer equals 1 year of snowfall. So scientists can go back in that ice core and count layers and help them date it. The scientist on the right is marking up an ice core to be shipped to the ice core facility in Denver. And in the ice core facility, those ice cores are processed. Half the ice core is archived for future scientists to study. And then the ice is cut up into pieces and sent to scientists at their institutions all over the country and all over the world to study. And there's lots of different ways to look at ice cores. So what can we learn from ice cores? This scientist is getting ready to cut just a round off the end. And if you cut a round off the end and hold it up to light, you can actually see the air bubbles that I was talking about that are trapped in there. And from those air bubbles, scientists are able to take a measurement of carbon dioxide. In this is an 800,000 year continuous record from ice cores from today on the right, back 800,000 years, almost 1 million years of carbon dioxide record. Up the side, left side are the carbon dioxide in parts per million. So I want you to notice that it goes up and down in kind of a fairly regular pattern. And especially want you to notice this, that in the natural world for 800,000 years, the parameters have been about 180 parts per million on the low side to 280 parts per million on the high side. So at the 280 parts per million, that's an interglacial period, warmer world with higher sea levels. That's the part of the warmth that we're in now. We don't have ice ages right now. We have ice at the poles. In a really cold world, at 180 parts per million is the carbon dioxide, tends to be in colder worlds with ice ages and lower sea levels, because a lot of the water in the oceans is now in the ice, in the ice of the ice age. But also notice that today, I went to and found out that our carbon dioxide today is at 411 parts per million, way out of the natural zone. And this is what scientists are watching carefully and are concerned about. Another thing that scientists are studying, this isn't from the ice cores, but this is global temperature, which is being measured all over the globe. The 5 hottest years on record have been the last 5 years. The 10 hottest years on record have all happened since 2010, or 8 of the 10 have happened since 2010, and all of the 10 since the turn of the century. So we're in a very hot time. And because of that, we're getting disasters increasing. This is a little bit older graphic, but I used it because it does a good job of using the US map and showing what kinds of disasters are happening here. And these are happening all over the world. But we've had a terrible time with wildfires in the West, flooding all over the place, more storms and more intense storms, hurricanes. We're experiencing this year in Florida more named storms than, except for one other year. It's the only year we've had to go out of the alphabetical list of naming storms and go into the Greek alphabet. And we're now there up to Gamma right now in the Greek alphabet, naming storms. We have more tornadoes, stronger tornadoes, all kinds of disasters. You've probably heard of the California wildfires out where Bill lives. Hundreds and hundreds of fires, and many of them are totally out of control. And the hurricanes that we've been getting that I mentioned. This is a graph of billion-dollar disasters and the years when they've been the highest in the US. I also want to leave you with a couple of thoughts. When I was a little girl, we didn't have computers, that's how old I am, but they did come in my lifetime. When my brother was becoming a computer scientist, the computers were huge rooms, supercomputers. Today, that technology has gone to a handheld computer in your phone that's more powerful than many of those supercomputers were. Think about energy, the technology of energy though. The energy back when I was a little girl, we would dig down and drill down and get fossil fuels from 60 sediments that were laid down 65 million years or more ago, the dinosaurs and the plants, pull up those fossil fuels, which would have taken millions of years to get back into the atmosphere. And instead we're burning them and putting them in the atmosphere in the last 100 years. But look at how the technology has changed. Oh, wait, it hasn't changed. It's the same technology. So I'd like to propose that we really need to move to sustainable energies as soon as possible and quit burning this, putting it into the atmosphere and adding carbon dioxide. But I'd also like to say that the news is not good right now about climate change. But there's a lot of opportunity. New energies equals new jobs, and we need to start making those things happen. And I want to leave you with a resource that I found. I was beginning to feel a little hopeless as a climate communicator until I came across drawdown.org. Drawdown means that point in time where we draw down concentrations of greenhouse gases in the atmosphere every year, starting to go down instead of every year going up. Scientists from all over the world came together in this drawdown project and came up with 100 solutions for battling climate change. The fantastic news, and the news that gave me such great hope, is that 80% of the solutions have the technology available today. 20% of those solutions are on the horizon and coming soon. So we're in a good situation to turn this around. But the big quote here is really important. This also comes from drawdown.org. Humanity's task is to accelerate the knowledge and growth of what is possible as soon as possible. So I'm going to turn this over to Bill now and let him get his computer going.
Thank you, Louise. Can you hear me?
Yes.
Perfect. All right, well, it's really nice to be with you guys today. It looks like from my screen, there's about 350 of us on the call from all around the world, and that's really exciting. I'm actually a retired science teacher. I wish I could see all your faces. It would be a lot more fun to see you, but instead I'm going to talk to this screen like we do in the Zoom world, and I'll pretend that you guys are incredibly entertained and incredibly happy right now. So that's how I'm going to go forward. I am going to ask you guys to participate with me today. We're going to actually be collecting data because my objective today is to talk to you guys about direct measurement data and then something else called proxy measurement data. So maybe you've heard these terms, maybe you haven't, maybe you're an expert in proxy data, maybe you're an expert in direct measurement data, but either way, I'm going to ask you to participate along with us, and we're going to actually do some data collection as a group. So no more sitting on your bed, you're going to have to get up and do some stuff. So you're probably here today for the same reason that I get on with people like Dr. Howley all the time to listen, because I'm concerned about where we're headed. I have kids, I have grandkids. I want to know where this climate is going. And that's probably why you're on here today also, because you're concerned about that. What's the next 100 years going to look like? So to know that and to be able to predict that, we have to know where the climate has been. That's how scientists make these predictions. So the better we can understand the Earth system and how all those pieces of the Earth system, the atmosphere, the oceans, how all of that works together, the better we understand how that's worked for the last millions and millions of years, the more accurate these scientists can be at predicting where are we going in the next 100 years. So they do that by looking at direct data and proxy data. So let's start by looking at these two types of data. And I'm going to start with the direct measurement data. And I'm going to ask you guys right now to do a couple things for me. I'm not sure quite how your setups are, but what I need you to do is, if you have access to it, a phone or a computer, I need you to find for your location what they're predicting the high temperature to be today and what they're predicting the low temperature be today. So do that, and then just since we're not like in a Zoom meeting, so I can't see thumbs up, but in the chat box, once you have it, can you just start typing okay, 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 and just type okay in the chat box. When I see a bunch of okays flying there, then I'm going to know that most people, all right, the chat box is flying. So everybody's got your high and low temperature. Next thing, got to do a little bit of math. I need you to get the average temperature at your location. Now, you're going to have to make your own decision on how you're going to do that. Like, I don't know if it warms up quickly during the day or if it cools off quickly at night, but I need you to do the best job that you can at estimating what you think the average temperature is going to be at your location, whether you're in India, whether you're in Africa, whether you're in the United States. And if you're in the United States, especially, you got to do one more step. You got to convert to Celsius. All right. So
we are getting a lot of responses.
Pardon me?
Yeah, we are getting a lot of responses. India, they say 25 because it's nighttime right now.
Perfect.
New York, 61. Yes.
We're going to get that. So Louise right now, if you guys could stop chatting, okay, because if you watch what Louise is going to do, she's going to post a link in the chat box for you. There it goes. She's going to keep posting that link as it scrolls up there. But what I would like you guys to do is this. Before you hit that link, let's do one other thing. That is a direct measurement. You can picture yourself going outside with a thermometer and measuring the temperature. Or in this case, we use the cell phone maybe to get the temperature, but all of those would be ways to directly measure the temperature today. I'm also going to ask you guys to do a proxy measurement. All right, now a proxy is this. That's an estimated temperature value based on something else that we can observe and measure. So here's what I need you guys to do now is here's going to be our proxy. I need you to look down at your feet. And I know me, if I look down at my feet, I'm in California. So here's what I'm wearing today. All right. I'm wearing flips today. So I need you to look at your own feet and say, hey, does the footwear that I'm wearing right now, does it resemble this? Does it have open toes? Or does it resemble that pair of Air Jordans? Is it nice closed toe where it's doing that? And those are the two pieces of data we're going to use. We're going to use your footwear as a proxy or as an estimate for what the outside temperature is. So now Louise is going to post a link in that chat box. There's the link. And I need you to go to that link, and I'm going to stop sharing my screen here for a second, and we're going to look at what happens. And I want you on this data chart, wherever you're at, I want you to type in your location and fill out that Google form so we know what the average temperature is on all these locations where you're sitting at today. And let me go back to share screen. And you can see as your data is pouring in, our average temperature is actually changing. You can also see, it's kind of cool, you can see where everybody's located. We'll give you guys about a minute more or so. Louise might want to post that link one more time for everybody. I do see a couple from New York that are posting 73. I'm assuming that might be Fahrenheit. So we might want to convert those to Celsius. If you look at the top here, we are getting the median as well as the average. So we might go with the median temperature because that'll throw out those highs and lows if somebody forgot to convert to Celsius. Hopefully climate change is not taking us to 70 Celsius or we could all be in trouble there. We're going to give you guys about 30 more seconds to get your data put in from all around the world. And thank you guys for participating here, getting in the game. And yeah, if you need to convert Fahrenheit to Celsius, you can always ask Siri. Siri does a nice job. You just ask Siri and she takes care of it for you. My chemistry students figured that out for me. I used to think it was a mathematical formula. Now it's just talking to Siri. All right. So it looks to me, I'm going to move forward. You can keep posting your data if you got it, but it looks to me like the median temperature right now for all of our locations is about 24.0 degrees Celsius. All right. And then here's the cool thing. If we go over and look at the form, your sandals, it looks like about 51% of you are wearing sandals and about 47% are wearing closed-toed shoes. So here's what I'm going to do. I'm going to take that data, I'm going to copy it, I'm going to put it right back into our little presentation here. So there is our proxy information. And then the actual direct measurement was 24 degrees Celsius. So let's see if this makes sense to you as far as understanding what a proxy measurement is. Now, my hypothesis is that if it was warmer out today, we're on all our locations, more people would be wearing sandals, less people would be wearing closed-toe shoes. If it's colder, you know, like I used to live in Chicago, if it's 20 below, I'm not going to be wearing sandals that day. So my hypothesis is those percentages would change. Now, as a scientist, what we would need to do is start to get a lot of data to see if that relationship is actually valid. And if it was valid, then we could start to use what type of shoes people are wearing as a proxy or as a way to estimate the temperature if it was impossible to actually go out and measure the temperature. So that's how these proxies work. So in this case, if it was true, I could say, oh, well, when we have 53% of the people in sandals, that's equivalent to about 24 degrees Celsius. So let's see, what do we do with that data? Well, if we get a lot of data, our models become a lot better. So here is, you can take a look at this. This is direct measurement data. So it's not a proxy, just straight up direct measurement of global average temperatures over the last 100 years or so. And remember, the goal here is, as we look at this, all of this data is helping us to predict where we're going. So see if you can just visualize some trends in this as you're watching these colors change. Any of the red areas are obviously above averages. Any of the blue areas are below averages. And there's where we were at in 2018. So this data, you can look at it a couple of different ways once you start to collect it. But again, our main goal is to predict where we're going. So here's another way to put that. Our average temperatures for the last 100 years or so look something like that. You say, okay, well, that's interesting, but if I want to know really where we're going to go in the next 100 years, I need to put that in perspective. Where have we been in the past? So now we have to turn to these proxy measurements. So let me show you another example of a way that scientists can use proxies to get a better estimate of where we're going. Maybe you're familiar with these tree rings. If you've ever cut down a tree, you can see that they have all sorts of growth rings in there, almost like the ice cores that Louise showed you. Well, these rings, it actually turns out some years the trees grow more, some years the trees grow less. And there's a relationship between temperature with that. The trees like it when it's nice and warm. They don't like it as much when it's cold. So we could use tree ring width, and scientists do use this as a proxy for what global temperatures were when there was nobody around to actually stick a thermometer out. So if you look at like a section of tree like that, even from like 1,000 years ago, once you establish the relationship, that proxy relationship, now we could actually take some tree rings like that and we could turn this into a temperature graph. Anytime you have really wide rings, we're going to say, oh, temperature on the planet was probably pretty warm, or at least the temperature at that location where those trees were. Well, with that information, we can start to get a better picture of where we've been so we can predict where we're going. And using tree rings and some proxies like that, we can go back 1,000 years or more. And now we start to get a better picture of where we're going. But really 1,000 years isn't enough to predict where we're going for sure the next 100 years. So scientists look at other proxies. So this is why people like Dr. Hawley go all the way to Antarctica, is because they're going to use something as a proxy for temperature called isotopes. Now, oxygen atoms, I'm sure you've all heard of oxygen, you've heard of hydrogen atoms, you've heard of water molecules. All oxygen atoms are not the same. Some oxygen atoms actually come with 2 extra neutrons, which makes them a heavier isotope of oxygen. Well, if you have a water molecule made with that heavier isotope, that water molecule is a little bit heavier too. So they call that oxygen 18 as that heavier isotope of oxygen. Most water molecules have just regular oxygen 16 with the normal or more abundant number of neutrons and protons have, but neutrons. So here's what we have found out is by measuring snowfall today, we have established this relationship. When it's warmer outside, the snow has more water that contains oxygen 18 in it. When it's not as warm out, when it's cooler, the snowfall has less water in it with oxygen 18, and it has a more abundance of water with oxygen 16. So because we can measure that today, we can establish that relationship. We then can use that as a proxy for temperatures going back in all of these ice cores that they're pulling up. Well, that allows us to really start painting a better picture, because now we have an 800,000 year record of what the temperatures on the planet have done when different parts of this atmospheric Earth system have changed. And again, if our goal is to fill in that last little piece, where are we going in your lifetime? Where are we going in the next 100 years? Now we have 800,000 years from these ice cores where we understand that Earth system. And people like Dr. Hawley can start to make some pretty confident predictions. And here's what we predict. Based on 800,000 years of temperature data and atmospheric data, this is where it looks like the planet is headed in your lifetime. So before I turn it over to Dr. Bob, let's just look at these things. We've talked about proxy measurements, and all proxy measurements are substitutes or estimates when you can't actually make a direct measurement. And the scientists over with the ice cores have used isotope data, not only oxygen isotopes, but these hydrogen isotopes. They have all sorts of different proxies So they start to gain a lot of confidence in their predictions of what temperatures were like, even when we couldn't make a direct measurement. They also use direct measurements on these ice cores. Like Louise said, these trapped gas bubbles allow them simultaneously to make direct measurements. Since that's actually the atmosphere trapped in those bubbles, they can actually go in there, get the gases out of those bubbles, and they know exactly by direct measurements, just like you guys got the temperature today, what the atmosphere was like 800,000 years ago. And then they can start to use those two to better predict where we're going. And based on all of that data, the direct measurements, the proxy measurements, this is where we think our planet is headed over the next 100 years in your lifetime. So like Louise says, there's a challenge there and there are solutions. It's up to this generation is going to be the one that fixes it. And the other thing that these changes are already, changes in temperature already doing is they're impacting the polar regions. And that's Dr. Holly's specialty. So with that, I'm going to stop sharing here and I'll turn it over to Dr. Bob, and he's going to share with you some of the observable changes that we're actually seeing in these polar regions today. So let me, if I can stop sharing. There you go.
Great, thanks, Bill. Well, that was these two are fantastic sort of setups for what I'm going to be talking about, which is primarily what we're actually seeing as changes in the Antarctic and the Greenland ice sheets. So hopefully you can see my screen here. See my presentation? Give me a thumbs up, Bill or Louise. Okay, great. As Paramita said, I'm a glaciologist, and what I fundamentally do is study the Greenland and the Antarctic ice sheets. And in addition to looking at ice core measurements of past climate, one of my specialties is understanding what these ice sheets are doing today. And so today, I'm going to take you through, first off, what a glacier is, how a glacier works, and how an ice sheet and a glacier are related to one another. Then I'm going to do a little bit of a slideshow travelogue about what is a glaciologist and how do we work. And this will address some of the questions I've seen coming through on the Q&A about how do you get around, things like that. And then finally, I'm going to bring you through two specific projects that we've been involved in where we're addressing the mass balance of the polar ice sheets and how the ice sheets are gaining mass and losing mass and kind of what's happening. Because most people these days are thinking about the ice sheets in context of sea level rise. So to start with, what's a glacier? Oh, and I should point out that because I've got full screen, I'm not able to see the chat. And so Bill, Louise, or Paramita, you can interrupt me if I need to be interrupted for anything.
Yeah, there are some interesting questions, but I was thinking after the presentation, we will discuss them.
Yeah, I'll make sure to leave at least a good 10 or 15 minutes for questions at the end.
Okay,
great.
Sure.
So what is a glacier? Many of you have probably been on a glacier. The question is, how does a glacier really work? So here is an example of the Blue Glacier, which is a glacier in the Olympic National Park in Washington State. You get snow falling high in the mountains. A glacier is essentially ice in motion. And so the way a glacier works is up in the high elevation areas of the mountains, snow will accumulate. Can you see my mouse here? Give me a thumbs up. Great. Snow will accumulate in this upper region of the mountain. In places where it's cold enough or where there's enough snow, that snow remains from year to year. And as more snow gets piled on top and more snow gets piled on top, eventually it compacts down into the form of solid ice, and then it starts to flow downhill. And so there's flow down this hill, very much like any other type of fluid, like honey, except that it's just very, very slow. People will say, oh, we're moving at a glacial pace. In terms of Earth science, glaciers actually move very fast compared to things like moving plates and plate tectonics. The glacier flows downhill, and it flows downhill enough until it gets into a warmer region where there's melting during the summer. And what happens in the summer is you get a net loss. Oops, sorry about that. You get net loss in the summer. So it's essentially, you've got mass gain, snow and ice is gained in the accumulation area. It flows downhill into what we call the ablation area, or the loss area, and it melts there. right in the middle of the glacier, or physics-wise in the middle of the glacier, there is a spot where the gain and the loss are equal to one another, and we call that the equilibrium line. So that separates the accumulation area up above from the ablation area below. Luis talked a little bit about how snow becomes ice, and this is just an illustration to depict how the snow in this upper left-hand corner is individual grains very much separated apart from one another. They then start to get settled and then sinter together, very much like a clay will compact in together to form a bowl or any type of pottery. Eventually, those grains get sintered together and are sealed off, and you get these bubbles that Bill was just referring to. Those bubbles are trapping the atmosphere from when those bubbles formed. And so this is one of the ways that that snow and the ice on a glacier retains the characteristic of the atmosphere that was present when the snow fell on the glacier. And in some cases, that can be up to 800,000 years ago, as we've seen. So you see, as we go down in depth, this is a snow pit on the Greenland ice sheet. We go into greater and greater depth, you can see these layers. And this is an example. This is about 1 meter deep, or about 3 feet deep. And in this example, you can see light layers and dark layers interspersed. These light layers and dark layers are the different seasons that go through. So you've got a summer season, a winter season. So you can count these layers back in time very much the same way Bill was talking about tree rings, where you can count the tree rings back in time. You can also count the layers back in time. So we use those when we're looking at ice cores, and also when we're looking at mass balance. So for example, I can tell you that in this particular year, there was greater snowfall than in this particular year. So we're in the accumulation area this year. So I can use these layers as a direct measurement of how much snow fell. And so when we take this out into the size of an ice sheet, we can see that these ice sheets are really big players, and that the cross-sectional glacier of a mountain glacier that I showed you, if you just take that, this is my little schematic of an ice sheet. If you take that cross-sectional glacier and flip it backwards, you have an ice sheet. This is essentially how an ice sheet works. Up in the high elevations, you have accumulation area. There's an equilibrium line, just like in the regular glaciers. And in the lower elevation, you have an ablation area. And so ice accumulates here in the accumulation area, flows downstream towards the ablation area, and then ablates away. In the case of both Greenland and the Antarctic, that ablation, a lot of that ablation takes place in the form of calving icebergs. So you see, especially around the Antarctic, many, many calving icebergs. The other thing that makes this useful or interesting to us is that in the accumulation area, that is where we're getting more and more ice piled up year upon year, decade upon decade, millennia upon millennia, and that is why we can drill down through that ice to find measurements of past climate. So hopefully I've motivated you that going to the Antarctic or Greenland is a useful thing, and it's worth studying. And so next I want to go through just sort of a travelogue of how it looks to get to the Antarctic. This is the first stop of my friend Gary and I are flying to the Antarctic, and the first stop is New Zealand. Great place to go. And we're ferrying our luggage between the international terminal and the domestic terminal. In New Zealand, if you're working with the United States Antarctic Program, you get to a warehouse and they'll issue you with everything you need to survive this cold continent. So things that you might note are these great big blue boots, 6 pairs of really, really big socks, and a great big red parka. This big red parka is really ubiquitous around the entire continent. So you could show up dressed like I am right now, and they would outfit you with everything you need. In New Zealand, you don all of this clothing and get on an airplane. And of course, it is probably, 85 degrees Fahrenheit out there as they've got all this clothing on. So you sweat quite a lot on the airplane. On the plane, you're in pretty much first-class conditions. A lot of people chuckle when I refer to it this way, but I actually really prefer riding on planes like this. If you look at how much legroom Greg has here, my friend Greg, way, way more legroom than even in first class on a commercial plane. And so it is loud, but I've always enjoyed it. Eventually, we get down to the Antarctic and land on the ice. And these are, in the US program, again, we use ski-equipped LC-130 Hercules airplanes. These are airplanes that were designed in the 1950s. I like to think of them as the old Ford pickup truck of the sky. They can kind of go anywhere, and they can kind of get anything anywhere, but they are pretty rattly. When we go to other places that are much more remote, we'll take smaller planes. This is a de Havilland Twin Otter aircraft. And that can land almost anywhere, take off from almost anywhere. It has a lot less cargo capacity, but the accommodations are pretty similar. So we're here inside that airplane trying to fly to our next coring location. These are my toes right here in the foreground. But again, it's quite comfortable. You can see my friend Jay is sleeping very comfortably. When we're flying through the Antarctic, you can see amazing features. One of the great things here is that we're crossing the Transantarctic Mountains, and you can see the flow features where the ice is flowing through the mountains right here and here. You can also see on the coast, these are moraines. Basically, this is debris that's being carried off from these rock outputs called nunataks, and they're flowing down. So you can see the flow features in the glacier, which is really fun. And you can also see crevasses. Eventually, if we're going to a deep field camp, we'll land on the ice, and the first thing we'll see is effectively nothing. It's really an amazing feeling to be out there in the middle of the ice sheet with really literally nothing around you. So the very first thing we've got to do is set up our tents, because the weather can change in only a few minutes. One of the things I always do, I can't see the chat, but I will always, when I show this picture, say, okay, who knows what direction the wind was coming from? And the real clue here is, what direction is everybody facing? They're all hunched over with their backs to the wind. And that's one of the things that I've always felt in the Antarctic and in Greenland. That wind can change almost everything. This is an example of a very small field camp out in the Transantarctic Mountains. And we've got little tents, we've got our snowmobiles to get around. But I've also spent quite a bit of time in larger field camps. They're known as deep field camps, and they're established almost like a remote base. These little Quonset huts are called Jamesways, and they're, although they are essentially a great big tent, they are insulated, and inside it can get quite comfortable. Here I'm relaxing after a long day of work. There's a stove here which provides heat, and in fact, behind this blanket, there's even a shower. So it's definitely a little bit primitive, but it's still quite comfortable for many of us. This is Thanksgiving dinner at that same camp. This is a place called Seipel Dome in the just in the West Antarctic ice sheet. So we had turkey and pretty much all the trimmings. In fact, we had cranberry sauce from a number 10 can, and our camp manager built that cranberry sauce into the shape of the same Jamesways that we were staying in. So we had
those students, Bob, are they students? Yes,
there are students. So in here you've got a mix of, at this time actually I was a graduate student for this picture. So yeah, you've got a mix of students, professors, all sorts of support staff. There's all walks of life there.
Bob, there is one question from some students about the heating system inside the tent.
Yes. Can you say the question? Let me see if I can find it.
Paramita,
can you read the question to me?
Yeah. So the question is, in the chat they're putting, how are the tent heated up and what is the heating system in the tent? So I think from your temperature graph, they can understand more well. Yes.
Yeah. Okay. So in this great big tent, we've got a stove essentially, which runs on diesel fuel. So it's actually not very dissimilar to an oil heater in North America. These tents, which are the ones we sleep in, they're heated fundamentally by us. So there's no internal heater in there. We also get actually quite a lot of what I refer to as solar gain. The sun is up 100% of the time. In the Antarctic in the summer, the sun just circles around the sky. And so the temperature in the tent is actually quite a lot warmer than the temperature in the outside. So here you can see You got night, you've got day, and night and day. During the day, we've got our Celsius scale on the left and our Fahrenheit scale on the right. In the middle of the day, the tent can climb up to the 60s, the 50s or 60s. And so it gets quite a lot warmer than you might expect. So when we need to get around, there's a bunch of different ways on the ground. There's a bunch of different ways we go. Snowmobiles are pretty much the very ubiquitous means of transportation, but we also have these larger tracked vehicles. This is an example of one of these tracked vehicles loaded up for a traverse. So if you've ever been skiing at a ski area, you will have seen these. There's a full-on industry of tracked vehicles like this. This is called a Tucker Snowcat. It usually pulls grooming equipment on a ski area. But here we've got it loaded up to pull our cargo. Now, a funny story about this piece of equipment looks a lot like a monster truck. And so a friend of mine that was staying at the station saw me loading this stuff up and said, "Hey, I would like to ride around with you in that thing." And I said, "Absolutely, come on." And we're in a flat ice sheet. And so when we got moving, basically we were just staring at this. And you're driving about 7 to 10 miles per hour. And so it's just kind of like, and after about 10 or 15 minutes of that, he kind of was like, "I have no idea why I agreed to go along with this." When we don't have as much cargo to haul, we'll be using snow machines. And this is an example of getting into a field camp with a snow machine. But when you're out on the trail, finding your way on your own, there are times when there's just nothing out there in front of you. And that's a really remarkable scene. And I liken it, the best I can guess, is it's a lot like being out at sea, offshore, where there's no landmarks and there's nothing to guide you other than your global positioning system, or if you have the skills, you could use a sextant to make measurements of the angle of the sun.
What do you do for fun over there, Bob? What do you guys do for fun there?
Fun? It's all fun.
Snowmobile.
The research is fun.
Nothing else but fun. Right?
In reality, when we're there, we spend so much money to get there that we always bring more work than we could possibly accomplish in the time we have. And so we spend probably, I would say, 90% of our waking hours either doing the science that we're there to do, or doing the things that we need to do for survival, such as eating and sleeping. So almost everybody will bring books because there's times that you get stormed in. People will bring games. Occasionally people will have, we have laptops with us, and so sometimes people will have a hard drive full of movies and they'll watch a movie. So
somebody asked, do you fish? You have ice fishing?
That's a great question. So here we are on an ice sheet, and we're about 1,000 meters of ice below us. So it would be very, very difficult to drill through. And even if we did drill through, what's under that is land. So in this case, there would be no fishing to be had whatsoever. One of the things that I did early in my career was spend the winter in Greenland, in the center of Greenland, at the place called Summit Station. So this is a small station, and there were 3 other scientists in addition to me. You get closer up, you can see that this is a small building. It was originally built on the surface, but it very quickly got drifted in. This drifting snow comes from blowing snow. The wind has blown all the way across the ice sheet and has settled down right up next to the structure. Fortunately, we have large pieces of equipment to help us dig this out. We don't have to dig it all out by hand. And so we've got lots of help that way. The best thing about spending the winter in the middle of the Greenland ice sheet was the Aurora Borealis. If you've ever seen these, the Northern Lights, it's just amazing colors and so incredibly dynamic. And it's absolutely worth, if you ever have an opportunity to see it, I highly recommend it. So I always end my little slideshow travelogue with this picture of my colleague Gary, because I want to give you truth in advertising. I'm probably one of the most field-going glaciologists that I know, And even so, I spend at most 2 months of my year working in Greenland or the Antarctic. And the rest of that time as a scientist, I spend basically doing what Gary's doing here, sitting in front of a computer, scratching my head and thinking about the data that we've collected. So I want to take you through some of the stuff that we've learned on some of these expeditions. And what we're fundamentally looking at in a lot of these expeditions is the mass balance of the ice sheet. And I've referred to mass balance a few times. And what I mean by that is the balance between the accumulation on the ice sheet and the ablation of the ice sheet. And what that really means to you is there's a bunch of water stored up as ice on land, right? So there's all this water locked up in the ice sheet. If that ice sheet grows, and the other great big reservoir of water on the planet are the global oceans. So if this ice sheet grows, as it has in the past, you'll see a drop in global sea levels, as we have in the past. During the last great ice age, 15,000 years ago, sea level was significantly lower, and we have evidence of that. Currently, in the current climate, as the ice sheets are shrinking, there's ablating liquid. The liquid is melting off of the ice sheets, it's entering the oceans, and sea level is rising. It's because of it. So we want to be studying that mass balance between the growth and the shrinkage of the ice sheets. And so we do that in several different ways. And the first one that I want to tell you about is something looking at the accumulation part of the Greenland ice sheet. This was a traverse where we spent 2 seasons, about 16 weeks total, driving snow machines from this station called Die 2 on the southern part of the ice sheet, all up through this route to the summit of the ice sheet. That was the first year. The second year, we started at summit, came back down to the same spot, and did a great big triangular trip through there. And along the way, we drilled cores, which Bill and Louise have done a really nice job explaining how that works and what it looks like. And we also collected ground penetrating radar data, or ice penetrating radar data. And I'll talk about what that told us in just a minute. This is what our traverse looked like on our arrival back at Summit Station. This is me standing right there in the middle. And we've got all of our equipment that we needed to have for spending 2 months out in the middle of the ice sheet, we had to have with us. We have, this is our scientific equipment. This sled is completely full of fuel for our snow machines and for our generators. Here we've got food here. And these 2 little sleds here are our survival pods. For most of our time, we spent in camps, so we would set up tents. But if a freak storm would hit us, we would need to have these pods here in order to just clamber into those pods and be able to ride out the storm. Because once the storm hits you, there's not really enough time to put up a tent. So what did we learn? One of the things we were measuring is using ground penetrating radar. This is the surface of the ice sheet. It's a profile of the surface of the ice sheet. And we can send radar waves down through the ice. It bounces off of interfaces within the ice and then returns. And those show this layering. This is a zoom in. That show this layering very similar to what I showed you in the snow pit. Now, they are not annual horizons, but they are horizons that are constant in time. And so we can use those horizons to tell us what accumulation looks like. So what is the accumulation on the ice sheet? And the way we do that is we drill a core on one end, and using that core and using the isotopes that Bill talked about, we can get the dates for that core. So we can say, okay, this is 2016, 2011, 2006. We can go back in time, do the same thing at the other end, and then we trace the horizons along this radar profile from one core to the next. And in doing so, we can take the distance between horizons and the time between horizons, and we can find out exactly how much snow has accumulated between the two. And one of the things that we found on this particular expedition was that there's been a significant decline in accumulation since 1996, roughly 53% decline overall of our traverses. And this is at odds with what a lot of people have predicted, which is that in a warming climate, you should get more accumulation on an ice sheet. So that's something that turned out to be actually pretty important. And we published that in 2019 in the Cryosphere, which is an open science journal. So you can find that and read the paper yourself if you're interested. Looking at the ablation region, we were interested in trying to understand how the ice is flowing towards the coast. And one of the things that's happened more recently is there's melting at the surface of the ice sheet. This is a region close to the coast of the ice sheet, and you can see melt on the surface has accumulated in these ponds, referred to as superglacial lakes. When these superglacial lakes drain, it looks something like this. This is what's referred to as a moulin. That water gets down to the bed and essentially lubricates that interface between the ice and the bedrock and enhances the sliding. And so that makes the sliding go faster, and that makes the ice move into the sea more quickly. And so we wanted to study just how that was working. So again, we went out here. In this case, we're not driving snowmobiles around because there's lots of water, there's crevasses, there are moulins, there are lots of hazards. So we were airlifted out there with a helicopter and walked around on foot. We drilled a bunch of holes into the ice and we installed sensors. We were looking at ice motion. We were looking at how the water was changing at the bed of the ice sheet. And we were also looking at how the ice sheet was deforming. At the same time as we were doing this, we were also watching the ice sheet from space. So we had satellites that were looking at these lakes. And so here's our demarcation of where all these lakes are, and these are where our field camps are. One of the things you can do with these is you can see with these satellites, it's not quite as cool as in the movies where you're looking at people walking around in real time, but here we can see over a period of 8 days a pair of lakes that drain. So if you'll bear with me for a second, here you've got 2 lakes in the upper left corner. That's these 2 bright spots here. And if you follow where they are over this period of 8 days, you'll find that over time they've diminished and then they've disappeared by the end of that 8 days. So what's happened is that those lakes drained, and generally when they drain straight down to the bed. That water enhances the flow of the ice and moves it forward. But we wanted to check that. So we used this lake drainage data set that we collected and compared it to the velocity of the ice sheet at that spot. And here's what we found. So here is the velocity of the ice sheet on this side, and that is in this black line. In addition to the black line, so you see you've got some speeding up and then some big speed ups here. And it turns out those speed ups are associated with these large lake drainages that we see right here. The size of the lake drainage is indicated by the size of this red circle. So when you see a drained lake, you see an acceleration in the ice. And so that's been very interesting and tells us a lot about how ice flow is enhanced by that melting water. So go ahead.
Well, do you do any, I mean, we have a lot of chemistry students on. What kind of chemistry do you do there on those samples you collect on site?
So we don't do really any chemistry on site. Almost all of the samples that we collect are shipped back to Dartmouth. There's an ice core laboratory at Dartmouth. And the chemistry that we've done there, we've analyzed for major ions, we analyzed for trace elements, we analyze for particulates and for dust. And isotopes, of course, as Bill was talking about. Those are sort of the major sets of analysis that we do. And it depends a lot on what question you're asking. Like if you're asking the question of temperature, for example, then isotopes are probably your best bet. If what you want to do is determine what is the annual stratigraphy, then major ions are actually very good as well. If you want to know how atmospheric tracers of, say, biomass burning have changed, then you're probably going to be looking at trace elements. So there's lots of different things that we do.
Thank you.
Yeah.
Bob, there are some questions from the student. How can you identify crevasses? Suppose you're traveling on Antarctica. So mainly the crevasses, how you can sense that? This
is a great question, and it's actually very timely. We've now had 2 of my colleagues that have actually, unfortunately, perished in accidents due to these crevasses. And so it's something we take very, very seriously. And there's 3 things that we can do. One of the things that we can do is, I'm going to go back. If we come out to the ice sheet in a season like this, the crevasses are always highly visible to us. So there's no snow out here, This is all just bare ice. And any crevasse that's big enough to hurt you is big enough that you'll be able to see it very, very clearly. The other thing that we do is actually very similar to finding the lakes using satellite imagery, is we use satellite imagery to look for crevasses as well. And then finally, and that helps us decide what route we want to take. Finally, there's two ways of helping mitigate the danger due to crevasses once you're out there. If you have a great big vehicle, which a lot of traverses do, we didn't in this case, they'll put that radar transmitter, instead of dragging it behind the sled, they'll push it in front of the truck. And that will allow them at least a few seconds, the radar will be able to detect a crevasse. That'll allow them at least a few seconds to be able to determine whether or not there's a crevasse there. And then the last line of defense, and this is one that I have used on occasion, is you walk in pairs, very much like in the mountains, and you stay roped together. And so if one person is, say, 20 meters ahead, and then the person 20 meters behind is always ready, that if the person ahead falls into the crevasse, they can stop their fall and haul them back up. So that's our sort of crevasse.
Very interesting. Another
Yeah.
question is how the stratospheric ozone is dealing with temperature in Antarctica. Like, is it affecting any ice melt? I'm sorry. That was one of the questions I saw.
That's a great question. And stratospheric ozone, as far as I am aware, is not having as big an effect on temperature in the Antarctic as tropospheric ozone. So ozone in the stratosphere is really good at blocking some of the harmful radiation that we get from the sun. In the troposphere, so significantly farther down, ozone becomes a greenhouse gas. And so in the troposphere, you are seeing ozone as a warming agent, for sure. So I just have one last sort of summary slide on here, and then we can take it all to questions, which I'm really excited about. I love answering questions. So coming back to the balance between accumulation and ablation, when you sum that all together, this is an example of a study that was done that summed all of the mass balance pieces together, both for the Greenland ice sheet and the Antarctic ice sheet. And one of the things that you should notice here, so the black curve is the entirety of mass balance of Greenland and the Antarctic. The blue curve is Greenland, the red curve is the Antarctic. And on the y-axis, we have mass relative to 1990 about. And on the right axis, we have relative contribution to sea level. And so you can see, as the mass gets more negative, sea level goes up. And the most interesting thing I think here is that you find here we've got a steady decline up until right around 2005. And there's a very personal reason for that from my mind. I was paying a lot of attention here right up until 2005. And then in 2005, my first daughter was born. And suddenly I took my eye off the ball, and unfortunately, Greenland started melting more. But the main point of this curve that I wanted to show is that what I just read, just what I wrote in the title here, Greenland plays hard. The Antarctic is the elephant in the room, given that the Antarctic is the size of a continent. It's roughly the size of North America. Greenland is a much, much smaller spot in terms of the total reservoir of ice volume. However, Greenland is contributing much more than the Antarctic to the total sea level rise today. So with that, I just sort of come back through. I like to end my talks with a little retrospective of some of the things that you've seen. And then I'll just fire up this last shot of a thank you shot. Before I'll go back to the summary and conclusions. And then what I think I'll do is I'll leave this up, but I might escape the full screen of it. And or actually, you know what I'll do? I'll stop share so that I can see everybody, and I can happy to take questions. And I don't know, Paramita, do you wanna moderate questions? Would that work for you?
Yeah, I'm going to try. And if anybody else from the panel, if you see a question I'm missing,
We have one from Peter
definitely.
Chireko. Peter Chireko is one of our students who works at the U.S. Army Corps of Engineers. He did
Yeah,
a
Peter was in my class. Yeah,
he did a project on Antarctica with you, right, Paramita? So he asked a question about if the ice sheet melts, what would happen to the microbes and bacteria that are trapped underneath? He's asking about the micro fauna.
That's a great question. And as far as we know, there's nothing under there that we don't already know about, that we don't find in other places. But it is an important point that there are many frozen regions on the planet that once they melt, permafrost is an excellent example. Once they melt, they become part of the biosphere and start processing, and that changes the atmospheric chemistry as well.
There was another question. How long do you take for drilling the ice core?
It depends entirely on how deep you want to go and what kind of drill rig you're using. For the drills that we were using on the Traverse that I was talking about, we were able to drill roughly 30 meters in about one really long day, maybe 10 to 15 hours.
So 30 meters is how many, I mean, centuries you're looking, or thousands of years?
In that region of the ice sheet, we were looking for over 30 meters. I think we were looking at about 50 to 100 years. So it was a pretty short record. The main reason for that was we were wanting to look at the last few decades and seeing how the last few decades differed from the previous record. If you wanted to drill a really long ice core, like some of the records that Bill and Louise showed earlier, the 800,000-year record,
yeah,
those cores take years to drill. So first off, it takes a year or more to get the station established for drilling. And then once the drilling begins, it probably takes at least 2 years.
How deep do you go, Bob? How deep down do you go for drill? How deep do you drill?
And well, for the furthest drilling that I know of is about 3,200 meters. Louise, I don't know if you might have that number even from ice drilling office.
Unmute myself. I don't have it on the top of my head, but I can get it.
I think Ways Divide was the deepest that's been drilled so
far. About 12,000 feet. About 12,000 feet for US.
Yeah, absolutely.
Richard Alley talks about his 2 mile tour. Yeah.
Yeah.
One person from Heritage International, Sapna Gupta, asks about what happens to the salt in the sea when the water gets frozen? Does it settle down? Does it remain on top of the ice? This is Gupta from Heritage International Schools asking that.
So when sea ice freezes, there's 2 different things that are happening. One, some of the salt actually does accumulate in brine pockets in the ice, but most of that salt is rejected. And so that creates increased salinity in the seawater that's right adjacent to the ice.
There is another question, interesting. I'm just going to compose it, that how did you see the atmospheric composition in the ice record of the past? Like, what was the Earth's atmosphere like, or temperature wise?
So there's a couple of different ways we can see that, and the most straightforward ones, the 2 most straightforward ones Bill talked about. One of them is oxygen isotopes. So there is a relationship between the isotopic weight, in other words, the ratio of heavy to light oxygen isotopes in the water of the snow that fell, and that's related to the temperature at the time the snow fell. And the other really straightforward one is simply, as Bill mentioned, the measurement of the gas that's trapped in the bubbles as the snow turned into ice. And that is literally an example of paleoatmosphere. So it's a very difficult and tricky thing to do, to melt that ice and then trap the gas that comes out of it. But it is something they do, and that's one of the ways they're actually able to measure levels of CO2 from millennia ago.
Any past, record of CO2 spike, like apart from this Anthropocene?
That's a great question. I do not know of any, but I think that it's a challenge because the resolution of our records as we go farther and farther back in time is coarser and coarser. And so the kind of CO2 record that we have from the instrumental period over the last 50 or 100 years, if we go back, let's say 400,000 years into a very deep ice core, that is contained in a sample about 1 centimeter thick. And so that becomes very, very difficult to make, to try and see such very, very small spikes or very, very short duration spikes like what we're seeing today.
I have a question for my student, Jennifer Anderson, from my chemistry class. She gets extra credit for asking this question. How do you handle the waste, human waste there? That's a very important question.
This we learned in our workshop in summer.
That also depends entirely on where you are. So McMurdo Station has a wastewater treatment plant, which is exactly the same as anywhere else.
Okay.
Then other places in the Antarctic, because of the Antarctic Treaty, you can't leave anything. You can't leave anything, and so you bring a bucket, and you got to bring it. You got to bring it home, and it leads to lots of very humorous photos. Like I have a picture of there was a researcher at a camp in the Dry Valleys, one of the PIs, the principal investigators, a very, very highly regarded scientist, and he's about to get on the helicopter, and it's always chaos getting on the helicopter, and one of the graduate students ran up just as he was getting on the helicopter and handed him a cardboard box and said, "Take this back to McMurdo, it's very important." And the PI was like, "Okay, I will." And he's got it under his arm and climbing onto the helicopter. And the grad student has a picture of him climbing onto the helicopter with this cardboard box. And on the back of the cardboard box just says, "Poop."
When I got to Antarctica, getting ready to go out into the field, they handed me 2 Nalgene plastic bottles, not as fancy as this, but 2, one of them marked with a big P. And that's what it was for. You didn't want to get them mixed up. Remember, I said, always have a bottle of water with you. Well, you also had your pee bottle in your other pocket.
Yes.
Some students asked about the source of electricity in Antarctica.
What's the name of that student, Paramita? The name of the student?
Oh, I missed it. Like I saw a couple of questions. One recent one I saw was, yeah, but okay, I'll get it definitely. One is Surya Pratap. No, he said, what type of new energy shall we get from Antarctica?
That's
Is there
student,
anything we're expecting?
Yeah.
So I would argue that the biggest advances in energy in the Antarctic come about because we are trying to measure the environment, and we are also trying to not effectively smog the environment that we're trying to measure. And so when we're out there, we work really hard to use renewable energy sources. And so that is one of the places where we work a lot and really hard on things like solar and wind power. On another note, there are likely to be pretty big hydrocarbon resources underneath Antarctica, but at the moment, those are absolutely protected by the Antarctic Treaty. The signatories to the Antarctic Treaty agree that the Antarctic is only for scientific exploration, not to be exploited for natural resources.
And just to follow up on that, countries all around the world have claimed high pieces of Antarctica, but the treaty just says they don't recognize any of those claims. A lot of them are overlapping claims. They don't recognize any claims that it's hands off right now as long as the treaty's in effect.
Right.
There is a very interesting question to Dr. Hawley. Have you ever seen an iceberg fall into the water?
Yes, absolutely. And it's a really amazing thing to see, especially the large ones, because they're so large that they move very slowly. And so it can actually lead you into a false sense that there's actually nothing much going on. But as it turns out, there's so much mass moving that these large icebergs can generate really significant waves. And so if you are ever in a boat near a place where icebergs are calving into the water, you got to be very, very, very careful.
Okay, we have one other question I saw is, how do you get internet connection? I think Lennon was asking that, or Lennon was asking about opportunities. He wants to go, that's probably the student, he wants to go over there too.
So all the internet.
Lennon is a very good student, yes.
All the internet connectivity comes from satellites nowadays. And it's actually been a huge boon in the last, say, 15 years to be able to get on the internet from the Antarctic and from Greenland. When I started in the business, there weren't really practical satellite phones, and so we used HF radios, basically a ham radio, to talk with the main stations, and there was just no way of getting on the internet at all. So they actually had a network of ham radio operators that would connect people from the Antarctic to the people that they wanted to talk to in the United States. They called it a telephone patch. And so it was almost like the old time when you had an operator, a telephone operator, always listening in on your phone call.
There are two very interesting questions. How much is the planet warming up? And then are there any other environmental concerns for Antarctica apart from the warming? I mean, apart from the glacial melt?
So what are the latest numbers on global temperature? Bill or Louise, do you guys know the latest numbers off the top of your head? I feel like I'm thinking about
the graph that I had up was based on the latest research I could find. You know, the estimates are between, I think, 2 and 4 degrees Celsius over the next 100 years, depending on what we do.
And it's difficult to make that kind of global average. It's a little bit like saying, what's the weather like on the Earth? Because the Earth is so varied and there's so many different pieces. That's one of the reasons why climate change is so difficult to get a handle on for so many people, because what's happening where you are is not the same thing as what's happening over the entire globe. So taking these averages is always a challenge. What was the other question? It was, what are the other environmental issues facing the Antarctic? So the Antarctic faces a lot of the same environmental issues that any natural area on the globe faces. So, but the good news for the Antarctic is it's still very clean. It has had its share, and it's still very clean, and there are a lot fewer humans making mistakes that make it dirty. You know, it has had its share of spills, problems like that. For some period of time in the 1970s, the United States ran a nuclear power generation facility there, but then that's been dismantled. But I think that's mainly it.
Dipti, you have any questions, Dipti?
No, it's okay.
Last question. There are a lot of questions coming, but I think we are also
Run out of time too.
Yeah. So last question was, I saw a very interesting question. How long can be an expedition, like where you can survive with the food supplies and everything when you go?
So I would say that's a lot like being on shipboard. So you can outfit a ship to be at sea for more than a couple of years. The longest expeditions that I know about that go without any resupply are on the order of between 3 and even up to 12 or 18 months. But those are generally stationary. I think that if you're trying to do some kind of traverse, you're unlikely to go more than 4 months without any kind of resupply, because you get to the point where you don't have enough ability to carry all of the food you need, and then you need more fuel to carry the food, and then it just becomes too much. So, for example, our expedition for 2 months on the ice, probably every 2 weeks, we came to a place where they had put fuel in a cache for us, and then we refuel our snowmobile. We put all of the fuel on our sleds and leave the empty fuel cans behind, where they would come and pick them up later.
So
thank you so much.
I can close out by asking students asking, how does one, I mean, countries come from Russia, people go from Russia, United States. How do you go to Antarctica? If I want to go and do research, let's say I'm from Trinidad and Tobago, I want to go and do some research over there. What's the process? How do you get over there?
So the main way of, there's two fundamental ways to get to the Antarctic. One is through a government, through some government that operates a research station there, and the other is as a tourist. And as a tourist, there's two ways. Both of them are very, very expensive. The one being on a cruise ship, which gets you right up to the Antarctic. And the other, you can actually, for I think $40,000, get on a plane in South America that flies you to the Antarctic. That's traditionally really only undertaken by mountaineers who are trying to climb the highest summit on every continent.
Yeah.
So these are very, very, like, they're throwing a lot of money at this. But the best way to do it is to become part of one of the national research programs. And you don't have to be a scientist to do it. This is the most amazing thing, especially in the United States program. A large majority of the people who go to the Antarctic with the United States program are in the trades and in the support category. So they need everything that you need in any town. They need electricians, they need plumbers, they need cooks, they need dishwashers, they need people who know how to drive the van. So they need everybody in addition to just a scientist. So you don't just have to be a scientist to go.
There's one question I would like to put forward. With all the research work that you all are doing, fantastic research work, how is the government using this research to basically bring in policy changes? Have you noticed that?
It's a really good question, and sometimes I have to admit that sometimes I will come back from one of these trips, I will compile all of the results, and I will write the paper, and then sometimes I'm disheartened by the fact that what I've written has not necessarily been collected and taken up by policymakers. There are so many different pieces in the realm of making public policy that the biggest thing I think that we do is we support these great big intergovernmental efforts, such as the Intergovernmental Panel on Climate Change. And it is a big, it's something like the IPCC that the policymakers really listen to. Probably more importantly, my biggest way of influencing policy is one of my PhD students who graduated from his PhD with me and did work on the ice with me, now works in Washington, D.C. As a science policy analyst. And so he actually is in D.C. working with policymakers to try and integrate more science into the policy.
Students are asking for your last words to people who think climate change is mythical and not real. What's the message from you to them?
My message from me to them is you need to look very hard at the motivation of the people that you're talking to when you're listening to the arguments. And so the two things to look at are, one, what are their credentials? Why do they understand climate? And two, what is their motivation? Do they have a reason to benefit from whether there's climate change or not? And I guess I would argue, some people have said that people like me benefit from climate change, and I think that's absolutely not the case. If there weren't climate change, I would still be a professor at a college teaching science. I really wish it didn't happen, and I really hope we can fix it. And there's not any money to be made from this. On the contrary, there are many industries who feel their livelihoods are threatened by the issue of climate change, and there's a lot of money, they feel there's a lot of money to be lost. And so there's a significant financial incentive to try and discount climate science. So I would say, look carefully at who you're listening to.
Before we close off the events, I know time is running short, so I just want to have a poll. We created a poll, so all the participants, we just ask you to, if you can, I'm launching a poll, so you can take a quick. It should take you 30 seconds to answer those questions in a poll. Can you let's do those questions? 3 questions. I'm sure less than 30 seconds. The poll. And the first question is, how do you rate this event? So I'm sure it's gonna be 5 out of 5, Bob. Don't worry, and Luis.
Absolutely. Absolutely.
Yeah, I can't vote.
It was really
my way.
very interesting program.
Sunaj, I hope you said give us 5 out of 5 here. Dr. Hans with his students and whoever is there. Dr. Pastor, Dr. Brennan, and all the students you have.
Neil, please share the results of that with us so we can
Absolutely.
Absolutely.
Yeah.
Yes.
Can you see the poll? Can you see the poll, Luis?
Louis, it was a wonderful email from Rose. I mean, yes, this morning I saw.
Yeah, 92%. Well, good job, 90%. So far, 92%, 90% gets a 5 out of 5. 5 rating, from 1 to 5 rating. In terms of what's the most important thing they learned, most people said what the conditions on Antarctica is like. That's 50%. Yeah, so it's very interesting. And what on the knowledge, on the question about the knowledge of ice cores and how it helps to understand climate change, on a scale of 1 to 5, let's see, 58% said yes, it really helped them to increase in knowledge connecting ice core and climate change together. So you guys did a great job. Thank you so much, Bill and
Yeah, thank you.
Bob
Thank you.
and Luis. You know,
Thank you so much.
to all wonderful students and Dipti and all the students in India and all the CUNY students who took part in this wonderful event. We really like to thank you for taking part in this event. This is wonderful. Paramita?
Yeah, thank you. So thank you to all, I mean, especially Robert Hawley, Louis Hoffman, and Bill Grosser. Thank you, Neil, for making this event, you know, creating the webinar. I know like morning time is to get called, like check your computer and see whether it's working or not. So he worked tirelessly. Thanks to all the students, all the faculties, especially from our department, who brought the students. Thanks, Dipti. Yeah, Yachit has logged off.
Thank you.
So thanks to everybody. It was a wonderful webinar. Thanks for your presentation. And you are now a part of our CUNY, and we look forward for more presentations from you.
So next time we see you guys, we come into Antarctica with you guys, right, Bill and Bob? Luis, you're gonna promise us a trip from you, Luis.
And
Antarctica,
and you all are welcome to New York.
Yeah, so thank you, everybody.
Did I see my students? Yes.
Thanks.
Thank
guys.
you.
It's been great.
Bye-bye.
Thank you so much.
Thank you, Bill. Thank you, Bob,
Thank you
again.
for this
Luis,
wonderful
great.
experience.
I'm gonna share the link of the video to everybody on Eventbrite and to Luis and Bob and Bill, of course.
Great.
Again, and Dipti, I'll send a link. Okay.
Great. Yeah. Thank you so much.
Thank you, everyone, and thank you, Provost Rapallo, for stepping in for the president as well. Thank you, everyone, again.
Excellent.
Okay. Bye-bye.
Bye.
Bye.
Everybody.